It's a pleasure for me to chair this session on mathematical physics today. Given the speakers and the occasion, I felt compelled to give longer introductions to each of them. But I'll restrain myself and give them more time to speak rather than the other way around. So please, we start having the pleasure to welcome Claudio Landim, who's a colleague of mine from IMPA, and he'll talk about variational formula for capacity on second-order elliptic operators. Thank you.
Thank you, Augusto. So I will divide my talk in three parts. In the first one, I will try to motivate the problem, to present the problem, and to give a bit of history. And once the problem has been introduced, then in the second part, I will try to present the results. And in the third part, I will present some applications of these results. So we'll start with giving you and just recall something about electrostatics. So for that, let's consider you have a body, A, and you know by Coulomb law that if you have two charges at x and y, of charge q1 at x and q2 at y, well, you'll feel a force which is proportional to the product of the charges, q1 and q2, and which is inversely proportional to the square of the distance. So if you have a body A and you place charges, say, at the boundary of A, and you call sigma the surface measure and sigma zeta z the density of charges, and if you consider a point, the total force felt at that point will be given by this integral. The force, it's a vector, so I'll represent the coordinates of that vector by f1 up to f3. And so at the beginning, in the 19th century, the problem was to compute this force from this explicit expression for general bodies. So you start with a sphere, and then you try to generalize that on. Up to a point in which Gauss proposed to change the perspective, and instead of trying to compute this force, try to characterize that force. So the problem I want to address in this introduction is the following. You have a body, and you consider that it's a conductor, so that the charges move freely on this body. And this body is immersed in a non-conductor, say glass or air, so that when you place charges, the charges will distribute themselves along the boundary of A in such a way that since it's a conductor, there will be no charges inside A. If there were charges, if there was force, the charges will just distribute and will try to split, and then they will hit the boundary, and at the boundary they can't move anymore because they are in this non-conductor medium. So my problem is once you place this charge in this body, these charges will be distributed along the boundary. It's to try to compute this distribution. So compute zeta for this distribution of charges. So here's the force. And to try to compute this zeta, let's first obtain some properties of these forces. So the first property that you can get easily by just taking the partial derivatives of f on A complement, so you take your out of your body A, and if I call nabla.f the divergence of f, you can, by taking derivatives here, check that the divergence of f is equal to 0. So the divergence being, well, you take the jth the derivative on the jth direction of fj, you sum, and you will find that this is equal to 0. So that's the first property of your field of force. There is a second property which is even more important, is that it's conservative. And what does that mean? That means the following. Well, you fix a point, fix a path on A complement which starts and ends at the same point, and compute. So the path is represented here by gamma, and compute the integral of f along this path. And what you can obtain is that, well, this integral is equal to 0. Right? Since this integral is equal to 0 along cycles, you can define the potential as follows. Well, you fix a point x0 in A complement, you fix any other point x, and you consider a path from x0 to x. You define your potential to be equal to C0 at this point x0, and then you just define f of x to be the constant plus the integral of f along this path which goes from x0 to x. And this is well defined. It doesn't depend on the path because the field is conservative, right? Whatever the path, you'll get the same integral. So this allows you to define this potential V. So here we have our potential. Mind that inside A there is no force because this is a conductor. If there was a force here, the charge will be rearranged in such a way to cancel that force. So the force inside the body is equal to 0. And then let's define this potential outside. So you have here the definition of the potential. If you plug F in this equation, you get this formula for V, where C is this arbitrary constant. Let's fix it to be equal to 0, so that you get this formula for V outside A. And inside A, you know that since F is equal to 0, V is constant, and the value of the constant is given by this integral. Well, now we can get an equation for the potential. Let me represent by nabla V the gradient of V, which means that, well, these are the spatial derivatives of V, so you get a vector. Well, from the definition of V as the integral of F, you immediately get that the gradient of V is equal to F. Now, if you recall that the divergence of F is equal to 0, what you get is that 0 is equal to divergence of F, but F is given by the gradient of V, and therefore you get that the Laplacian, which is this differential operator, it's equal to 0 out of A. So you get a formula for the potential. If now you're given boundary conditions, you can solve this equation, you get V, and from V you can try, you'll obtain F, and then from F you can try to get zeta, which is the distribution of the charges, which was our goal. So let me here recall. So you have your formula for F, you have the definition of V, which V and F are related by this equation. So in order to avoid problems at infinity, let me introduce a second body, B, which will be connected to the Earth, which means that B is connected to an infinite reservoir, so there can't be any charge on B. If you place a charge on B, since it's connected to the Earth, it will immediately go to this infinite reservoir, so there are no charges at B, and you define the potential. So again, this is a conductor, so there is no force inside B. V is constant, and let's define then V to be equal to 0 on B, and so the potential to be 0 on B, and given by this equation for the other points. So now you have the boundary conditions you need on for the potential. On the one hand, so let's represent by omega the complement of A and B. So I'll keep this notation throughout the talk. So the Laplacian of W is equal to 0 on omega. You know that on B it's equal to 0, and it's equal to some constant on A. So let's say that this constant is equal to 1, which means that W it's equal to the indicator. So I'll represent by chi A the indicator function of A. So it's equal to 1 on A and 0 on B. So you have your equation for W. From that, you can solve this equation and then recover the distribution of charges, zeta, by this equation in which NA will represent a normal vector which is orthogonal at the boundary points at A, and which is pointing outward. Right? So you can also, from this equation, or from the equation for V, obtain this relation, and this allows you to get the density for V. So you see how naturally, so this is a set of equations, it's called the Dirichlet problem, how naturally the Dirichlet problem arises in electrostatics. Now the problem was to solve this equation. And to solve this equation, Dirichlet proposed a principle, which is called the Dirichlet principle, which I will try to explain now. The idea is very simple. Let's define the energy of a configuration of charges. So this means that this is the total work you need to perform over your system to create this distribution of charges starting from an infinite dispersion. So you imagine that your charges are all at plus infinity, and then you bring them to form this distribution zeta. Well, if you have a finite number of charges, this is, you can compute, and you can compute the energy of a distribution. So if you have charges qi at point xi, you get this formula from the equation for the force. So in the case in which you have a distribution zeta of charges at the boundary, you get this formula for the energy of a distribution. Well, if you remember that V, it's given by this integral, you can replace one of these integral by V. And then if you recall that zeta was given by the gradient of V, this is the scalar product with respect to the unit vector NA, you can now replace zeta by 1 minus 1 over 4 pi of the gradient of V in this expression, and finally get an expression for the energy in terms of the potential only. And the idea of Dirichlet was that, well, what you expect from the distribution is that it will minimize the energy. So in order to get a solution of the Dirichlet problem, the differential equation which was in the previous slide, what you need to do is to minimize this energy among all potentials which satisfy the boundary condition. And this is called the Dirichlet problem. So if you want to solve this equation, you have a formula for your energy. You can integrate by parts in order to get to express this integral as an integral of the square of the gradient of V. So you have here an alternative expression for the energy of a potential. Well, in order to get a solution of that equation, consider this variational problem, and what he claims is that the function which minimizes that variational problem is the solution of the Dirichlet problem. And this, in the mid-19th century, was considered to be essentially a proof of the existence of the solution of that equation. But then in the 1870, Weierstrass found a counterexample, so a boundary which wasn't smooth, in which this statement of Dirichlet wasn't correct. And finally, in the end of the 19th century, Hilbert presented sufficient conditions for the Dirichlet principle to hold. Well, and it's very easy to see that, that indeed the solution of this variational problem should be the solution of the equation, because, well, if W minimizes, you take any F which is equal to 0 at A and 0 at B, which means that W plus epsilon F is also, satisfies also these boundary conditions. And since W minimize, this function as a function of epsilon assumes a minimum at epsilon equal to 0. And if you compute the derivative in epsilon, you get this expression, which means that this expression is equal to 0 for all F if W it's a minimum. You integrate by parts, and you get that this expression is equal to 0 for all F, which means that indeed the Laplacian of W is equal to 0. Okay, so this is the Dirichlet principle, and this is why this variational problem was introduced. With this, I conclude the first part of the talk. So this is to motivate this variational problem for the solution of that equation. So now, let's go to the potential theory. So what we would like to do in this talk is to generalize these principle for more general operators. So I will consider the d-dimensional torus to avoid problems at plus infinity. And I will consider an operator, a second-order operator, which will be written in the divergence form. So I have here a field, B. Everything will be assumed to be smooth, though it's not very important. Here I have a matrix, which depends on X. This matrix is also assumed to be smooth in X. But what will be important is that I'm assuming that it's strictly positive definite. Okay, so, which means that there exists a strictly positive constant C0, for which for all X and all Xi, we have this inequality. And I'm not assuming that A is a symmetric matrix. It's only a positive definite. And the point here is not so much the fact that you're extending from Laplacian to a general differential operator, but the fact that we want to consider operators which are not self-adjoint. So you see that if I take the Laplacian and integrate twice by parts, you get that Laplacian is self-adjoint. And here, well, the important generalization will be the fact that we are not assuming L to be a self-adjoint or a symmetric operator. And, well, these operators are closely related to some Markov process, which are solutions of some stochastic differential equation. So here, beta will represent a Brown motion, AS, the symmetric part of the matrix A. So this operator L, which was written in the previous slide, is the generator of this stochastic evolution. And in the sense, for those who are not from the field of probability, is that if you start at the point X, you let your process evolve up to time t. T is very small, and you consider test function f. Well, the average value of f of xt will be given by, well, f computed at the initial point. Then since t is small, you have a correction in t. And the drift of this correction is given by the operator applied to f. So this is the relation between this operator and this stochastic differential equation. So here is my operator. So the first important thing will be to find a reference measure, which will be the stationary state of that stochastic evolution. So it will represent by mu this stationary state. So mu satisfies this equation. Means that for any test function f, Lf integrated with respect to d mu will be equal to 0, and will well, normalize mu in order for it to be a probability. It's easy to show because we assume that A is strictly positive, that mu is absolutely continuous with respect to the Lebesgue measure. And so if you plug m in this equation, you integrate it by parts, what you get is that actually m is the solution of that equation, in which A star is the transpose matrix of A. You can show that the solution of this equation is strictly positive. So let me write it as m as exponential minus v. So the reference measure, it's actually exponential minus v dx. And using this exponential minus v, you can rewrite L in this form, where C is just B plus the transpose of A multiplying it by the gradient of V. The advantage here is that we have this relation for the field C. So the divergence of exponential minus Vc is equal to 0. And this equation, it's exactly this equation replacing C by its values. So all these slides, you can forget everything. Just recall that we have a general differential operator L, which is given by this expression, which is very convenient, and that will appear in the next slide, where the vector field C is divergence-free if you multiply it by exponential minus V, and mu is this reference measure. So here I recall L, and what I claim is that, well, this is very convenient because this second piece of the operator is skew adjoint. And you can check that by just writing f times this operator applied to a function g. Now you integrate it by parts, remember, mu, it's exponential minus v. So you have an exponential minus v here. When integrated by part, you have a piece which vanishes, and the other piece, it's just the gradient of f with a minus sign. So writing L in this term has the advantage that the second piece is skew adjoint. And if A were symmetric, the first piece would be self-adjoint. In this case, since I did not assume A to be symmetric, it's not self-adjoint, but it's very easy to compute the adjoint. So let me represent by L star the adjoint. So the adjoint of the first part will be just to take the transpose of A instead of A. And in the second part, as it's skew adjoint, it's just taking the minus sign. So we have an expression for the adjoint. And then from that, you can compute the symmetric part of the operator, which, well, these two pieces will cancel, and these pieces will produce the symmetric part. So now let's go back to our problem. We have our capacitor. We have distributions of charges on A. And let me represent the, what I would call the equilibrium potentials by H star in NHS. So remember, A omega, it's the complement of A union B. So these functions are the solutions of the Dirichlet problem. So LH, it's equal to 0 on omega, and H, it's 1 on A and 0 on B. The same thing holding for L star and from LS. In terms of our stochastic process, it's very easy to represent these solutions, the solutions of this equation in terms of a process. So if I represent by HA, the heating time of the set A, Hx, it's just the probability that starting from X, you hit A before you hit B. Now let's define the energy of this equilibrium potential. By analogy to the case in which we had the Laplacian, I will define the energy by this formula. So you see, since H vanish on B, I can add the integral of B, then integrated by parts, which I get this expression. And then remember that this piece is skew adjoint, while this piece, it's symmetric. So I can replace that piece by L minus the skew adjoint operator. The skew adjoint operator will vanish, and H is the equilibrium potential, so L of H is equal to 0. So that piece will vanish, and we'll get the final formula for the energy of the equilibrium potential to be given by this equation. And here I can replace A by the symmetric part. And here it's the place where you see that you have a problem in the case in which your operator is not symmetric, because everything which wasn't symmetric disappeared from the formula of the energy. So the formula of the energy makes only the symmetric part of the operator appear. Okay, so the variational formula, so if you try to minimize the energy over all potentials, what you'll get is the equilibrium potential for the symmetric part and not for the adjoint. So that doesn't work. You have to find a new variational problem which is satisfied by the equilibrium potential. So let me just call the capacity between A and B the energy of the equilibrium potential. And my problem is to find a variational formula for the capacity between two sets. And so here is the formula for the capacity. Before going to the variational formula, let's deduce some simple properties. The first one is that the capacity is symmetric in A and B. Well, that's easy because if you take A, B, A, and you take, well, H, B, A, it's equal to 1 minus HAB, because, well, they satisfy, HABA satisfy the same equation. L of HBA will be equal to 0 in omega, and they have exactly the symmetric boundary conditions satisfied by H. So you can replace in this formula HAB by HBA, and once you replace it, you get the symmetry. You can also start to integrate in by parts to get that the capacity of the adjoint is equal to the capacity of the original process. But then we can use the Dirichlet principle to say that, well, the energy of the energy, it's minimized by the equilibrium potential associated to the symmetric process. And from that, since this is the capacity of the symmetric, you get that the capacity of the symmetric is less or equal than the capacity, the original capacity. And this, well, it's a common knowledge that if you study the speed of convergence to the stationary state, that a non-reversible dynamics will converge faster to equilibrium than a symmetric one. And this is, in some sense, and that will appear later, a quantitative estimate of this fact. And now I come to the variational formula for the capacity. And to define this variational formula, I'll need to introduce flows. So I will define by F the flows. So these are vector fields defined on omega. And in this space of vector fields, I will introduce that scalar product. So AS, remember, it's a symmetric part of the matrix A. I take its inverse, and I take the scalar product, and this defines a scalar product among the flows. Among these flows, for any real gamma, I'll call F of gamma the flows which are divergence-free on omega. So if I take the flow and I multiply it by exponential minus v, I get a divergence-free flow in omega. And this flow transports a mass equal to gamma from A to B, which means that if you take the total mass flowing out of A, it will be given by gamma. The minus sign comes from the fact that the normal direction is defined incorrectly. So these are my flows F gamma, those who transport a mass equal to gamma from A to B. Then I have the set of functions which are equal to alpha on A and equal to beta on B. And two special flows which will play an important role afterwards, psi f and phi f, which are given by these expressions, which I don't expect you to remember. But just note that if I take the scalar product of psi f with psi f, so replace that here, and remember that psi f comes with the asymmetric, so one of them will cancel, and you get exactly the energy of f. So psi f gives you the energy of a function f. And now here's the formula for the capacity. So the capacity between A and B in the non-reversible case will be given by this double infimum. The advantage of having a double infimum is that it's very easy to produce upper bounds for the capacity. And you also have, you can also express 1 over the capacity as the infimum over flows and functions, and this will provide you upper bounds for the capacity. You can match these two upper bounds if you know how to approximate in your problem the equilibrium functions, right? The equilibrium potential H and H star, because you know exactly what are the functions and the flows which minimize these two variational expressions. So if you want sharp bounds, well, you will need to understand in your problem what are the solutions of those differential equations, or in stochastic terms, what is the probability that starting from a point you will hit A before you hit B. Knowing more or less precisely what are these functions, you can then find good test functions in order to get sharp lower and upper bounds for your capacity. So here are the variational formulas. Now, of course, you can recover the usual Dirichlet principle in the symmetric case, because you know, in this case, phi and f will be equal to 0. So you can recover from these formulas the variational formulas in the reversible case. And you can also produce a variational formula in terms only of functions, which were obtained before by Doyle and Pinsky. Then we've seen, so another remark that we've seen that the symmetric capacity is bounded by the capacity. Well, in case in which the generator or the operator satisfies a sector condition, you can get the other bound. So when the operator satisfies the sector conditions, the symmetric capacity is bounded below and above by the original capacity multiplied by constants. And with that, we end the second part of the talk in which we presented results. So now let's go in these last 15 minutes to some applications. One first application is about recurrence of Markov chain. So once you define a stochastic dynamics in some graph or some set, the first question you wanted to answer is to know if this process is recurrent or not. So let me give you an open problem to illustrate this question. So this is the Manhattan random walk. So what you do is the following. At each horizontal line, you choose a direction with probability 1/2. So either you only jump up or you only jump down in that horizontal line, and you do that with probability 1/2. You do the same thing for the vertical lines. So for each vertical line, you choose a direction with probability 1/2, and you impose that your walk will only jump to the right at one of these lines or to the left. Once you fix that environment, so this is an environment, assume it's fixed. No, fixed, given this environment, you consider a random walk. So you take a point. At each point of Z2, you have only two directions to which you can jump, right? Either you are on the horizontal line in which you can jump only down and only to the left, as in this case. And at this point, you choose one of these two points with probability 1/2. And that defines your dynamics on this random environment. And the question you ask is, well, start from the origin. What is the probability that you'll return to the origin? So call H0. So this is a discrete time dynamics. And call H0 plus the return time. So the first time we return to the origin after starting from the origin. And you'll say that it's recurrent if the probability that you never return is equal to 0. Okay? These formulas, which I presented for the capacity in the continuous setting, have versions in the discrete setting. And in the discrete setting, the formula for the capacity is given by this expression. So M, it's the stationary state of your process. So you're summing over all points in A of the stationary state of X, multiplying the probability that starting from X, you hit B before you return to A. So this is the expression of the capacity in the discrete time setting. And you see that here I'm interested in returning to the origin. So let's consider a sequence of sets Bn, which contain the origin, which are finite, and which increase to Z2. So saying that you never return to the origin means that you will hit the boundary of this set Bn before you return to the origin. Now if I multiply that by M0, and I compare this expression with the capacity, this is exactly the capacity between 0 and B, the complement of Bn. So in order to prove that this is equal to 0, what you have to show is that the limit of this capacity is equal to 0. Which means, since we have upper bounds for the capacities, that if you want to prove that it's recurrent, you have to find flows and functions which permit you to show that this capacity goes to 0 as n goes to infinity. Or if you want to show that it's recurrent, you need also to obtain flows test and functions, test functions, which permit you to show that this is strictly positive. So this gives you a rather efficient tool in order to show that processes are either recurrent or transient in the discrete time setting. And it also follows from that inequality, you see that if this capacity is going to 0, the symmetric capacity is also going to 0, which means that, well, if the process is recurrent, then the symmetric version of this process is also recurrent. And you have the converse, if the symmetric is transient, then the process is transient itself. And this has been used recently by Hermon and Benjamini for proving that the non-backtracking random walk it's recurrent or transient for certain graphs. So this is an efficient tool in order to solve this type of problem. So this is one type of application. Second type of applications are about transition times. So here I want to understand my stochastic evolution as a small perturbation of a dynamical system. So I want the noise here, which is being added to the differential equation, to be small. So it will replace A by epsilon A, where epsilon will converge to 0. And in order to keep this term, I will replace V by epsilon minus 1 V. So I get this new expression, which now depends on epsilon. So this is a small term, so I want to interpret this stochastic differential equation, this evolution, as a small perturbation of this dynamical system. And for this dynamical system, I want the potential to be a Lyapunov function. So in order for V to be a Lyapunov function, I need to add this condition on the vector field C. So remember, I had this previous condition on the vector field C. So from now on, I'm assuming that C is orthogonal to the gradient of V, and that the divergence of C is equal to 0. And I'm considering this evolution, in which, remember, that the stationary state is given by the exponential of minus V, but now the potential is being divided by epsilon, which means that the stationary state will concentrate it on the minima of V. So the potential V I have in mind, it's a potential which has some local minima and a global minima. We could have more than one global minima. And the question which was asked by chemical physicists at the end of the 19th century related to chemical reaction was the time it takes from this process, starting from from a point which is close to a local minima, to jump to the global minima. So what you expect, since V is a Lyapunov function, it's that starting from this well, you will follow the dynamical system, which will drive you to these local minima. You will remain there for a very long time, and due to these fluctuations, which are very small because I'm multiplying the Brownian motion by epsilon, you will remain there for a very long time. You will equilibrate over there, and then you will jump to, after large fluctuation, you will jump finally to this global minima. And the question was to obtain estimates of the time it takes. So here's so starting M1 will be this, say, this local minima. V will be a neighborhood of the global minima. And Arrhenius proposed, by microscopic considerations at the end of the 19th century, the following formula for this transition time, which is now called the Arrhenius formula, that at the exponential level, so this time was exponential, as exponential constant divided by epsilon, and that the constant, called delta, was given by the difference of the potential computed at the saddle point. So sigma will be a saddle point, and M1 will be the minimum. So that was the first order approximation of this transition time. And then, well, one could go to the second order expansion of this formula, computing P. So you can go up to the second order P. So this epsilon will cancel to this 1 over epsilon. So you have here exponential P, which I'm writing as small p. And small p will be given by an expression which depends on the Hessian of V around sigma and around M1, and one eigenvalue of this, this matrix. And here again, you can show that if you take the symmetric version of this dynamics, lambda s, it's less or equal than lambda, which means that the transition time in the asymmetric case, it's shorter than the one in the, for the reversible dynamics. So you go faster, you jump over this energetic barrier faster if you consider non-reversible dynamics. And so this is called the Eyring-Kramers formula, and it can be proved using these estimates on the capacity, because you can express these times in terms of capacities. And by using the variational form of the capacity, you can obtain these precise formulas. So this was done in the 19s and 2000s explicitly by with different methods in the reversible case. And it was predicted by Boucher and Régnier for the asymmetric and proved recently in the asymmetric case. So now I want to go to a third application, which is about metastability. So, se puder mostrar. So let me show you a video. So what's happening here is that you have water, which is supercooled at -2 centigrades. So this water wants to become ice, but it's still water. And then when you perform some type of perturbation, immediately it becomes ice. And this is exactly how beer is drunk in Brazil. So you cool it down up to -3, and then you pour it slowly in your cup, and you have to do it very slowly, otherwise it becomes ice. So you can try that in bars here in Brazil. And so what you have, it's you have some object which is in a metastable state. So you believe that it's in a stable state because it can stay there for very long. So this water, this supercooled water, could stay water, behaving as water for a very long time. But then some fluctuation immediately creates a change in its state, and it goes from, in this example, from water to ice. So there were many models, stochastic models, introduced in order to model such a phenomena. So here I want to present one which is called this condensate zero-range process, which was introduced by Evans in 2004, and in which you have particles moving in a graph with L sides. So L is fixed, you have L sides. You place n particles, n will converge to plus infinity, so it's very large. And the dynamics relies on two parameters, one which is p, which is a parameter between 1/2 and 1, and a function g. So this function g tells you the rate at which one particle will jump from one side to the other. So g at 0, it's say 1, g at 1, so okay, this is 0. It's a mistake here, g at 0 is 0, g at 1 is 1, and then g for n larger than 2, it decays. So alpha, it's a fixed parameter greater than 1. So you see that gn, it's strictly positive, and as n goes to infinity, it converges to 1. So it's something which is decaying to 1. As I told you, g is the rate at which a particle jumps from one side to the other. The fact that it's decreasing means that the more particles you have, the slower you jump. Okay? And then once you decided to jump, you'll jump to the right with probability p and to the left with probability 1 minus p. If p is equal to 1/2, you have a symmetric dynamics. If p is greater than 1/2, you have an asymmetric and non-reversible dynamics. Then say that you start with an even number of particles at each side. You let the process evolve. And what's surprising, at least it was surprising to me, is that instead of staying in this way, that with even particles distributed at all sides, what you have, it's a condensation phenomena, which means that if you wait long enough, all particles will remain at one side. So essentially, the n particles will stay at one side, and you have a few particles moving around. And actually, if you represent by mu n the stationary state of this process, and if you take a sequence Ln, which increases to infinity but slower than n, you can show that the measure of the configurations in which you have essentially all particles at site x, so let me call Ex the configurations in which you have more than n minus Ln particles at x, well, that the measure of this set is converging to 1/L. And since you have L sites, which means that, well, the measure is concentrated on those configurations. Right? So since this is the case, what do you expect for these dynamics? Well, you'll have all these, essentially all particles on one side, few particles moving around. The system will stay like that for a very long time, and at a certain point it makes a transition in which all particles decided to jump to a new site in which they will remain there for a very long time. So you have a phenomena which is very close to the one I showed you in the video. You remain a very long time in one state, and then suddenly you make a very quick transition to another state in which all particles stay in U. And so what you wanted to do is to formalize that. So you want to represent these dynamics by a simpler one, which tells you only at which site all particles are. So where is the condensate? And to do that, well, what you do is that you define this projection. So if you have a configuration eta, if eta belongs to Ex, which means that if all particles are essentially at X, you call that X. And what you prove is that if you observe your dynamics at a time which is n to the power 1 plus alpha, where alpha is this parameter, then this process, which is not Markovian anymore, will converge to a Markov process in 1 over L. And this, I mean, the proof of this statement relies on the estimate of capacities, because the capacities will give you essentially the rate at which you jump from one configuration, one set to the other set. And so based on that variation of formulas, you're able to prove this type of statements for that model and for many others in which you have this phenomena. So the phenomena is described by two properties. The first one is that you remain in a set a very long time, long enough in order to equilibrate in this set, and then you do a very quick jump to a new set in which you remain a very long time, in which you equilibrate before you jump to a new set. So with this idea of metastability, that you remain a very long time, long enough to equilibrate inside this set before you jump to another configuration. And I see that I'm over time, so I think I'll stop here. Thank you for your attention.
So we have time for one question.
Hi. Can you say something about the time it takes for this last transition? The distribution of the time, or so, the size of the time?
So in this model, the time it takes to equilibrate, it's n squared. See that alpha is bigger than 1. So you equilibrate inside the set in time n squared, and then you jump in time n 1 plus alpha. So alpha is fixed. It's a fixed parameter given at the beginning, and it's bigger than 1. So this parameter is fixed. And so what I say is that if you want to see a jump from one side, well, all particles from one side to the other, you have to wait this order of time, n to the power 1 plus alpha. But if you want to equilibrate inside one of these sets, you do that in n squared.
So do you expect the same thing to be true on any finite graph? And does the
yes, that has been proved,
and it's proved
for any finite graph with fixed number of sites.
Oh, right.
The number of sites is fixed, but it works for any graph.
Okay.
So if there are no more questions, let's thank Claudio again.